Okay, good morning. The focus of my talk will be on the formations of the disks, which are, of course, the bridge that connects the star and planet formation. So you may think that disk formation is a simple, perhaps even a trivial consequences of the angular momentum conservation during the core collapse. So I would like to, at least I hope to convince you, though, that in fact, the disks are relatively difficult to form in the presence of a dynamically important magnetic field that's often observed to threat molecular clouds, like in the case of the torus in the background, and like what the Zhi-Yun Li told you yesterday. So the first half of the talk will be on the basic theoretical difficulties in forming disks, starting from the conceptually simplest case of the ideal image limit, where we now know that from both the analytical consideration and numerical simulation, in fact, disks formation is suppressed completely in dense cores magnetized to a realistic level, and the non-ideal MHD effects that we know must be there, in fact, in general, would not be able to help the formation of the large Keplerian disks, at least under the assumption of the axis symmetry. In 3D, it turns out that the problem persists, although there's a new effect. It turns out that the magnetic flux dragged into the central region will drive the inner accretion flow unstable, so making that region much more complicated than envisioned perhaps so far. So the second half of the talk, I will review the various proposals that's on the table now, trying to form disks in magnetized cores. So just like Mark Homos, I also like dimensions numbers. And the one that I'm going to talk about again and again is this lambda. It's the mass-to-flux ratio. It's just the mass of a given region divided by the magnetic flux thread in that same region, normalized by this critical value. Now, I want to remind you that the larger this lambda, the larger here, the weaker the field. Now, if lambda is greater than 1, that means the magnetic forces by itself would not be able to support against the gravity. That region will collapse. And that actually seems to be the case for dense cores, according to Cholan and Crutchard, who actually measured the line of sight component of magnetic field through a sample of dense cores. So this measured the line of sight component, by and large, they are less than the critical value. And probably the typical value, well, the mean is about maybe 1/5, 5 times smaller than the critical value. But of course, the total field strength is somewhat larger than the line of sight component. So the typical field strength is probably about half of the critical value, which means that the magnetic field by itself would not be able to prevent the collapse of the core, which of course is good news because you want to form stars. But it does contain more energy than the energy in the rotation, which is typically only a few percent. So magnetic energy is probably tens of percent. So it should not come as a complete surprise that the magnetic field would change the angular momentum evolution, will interact very strongly with the rotation. And in fact, I'm going to argue that it could actually suppress this formation, at least in the simplest limit of the ideal MHD. Now, the argument is the following. If you assume strict ideal MHD, which means that the magnetic field lines has to go where the matter goes, it's completely frozen into the matter. So if you have a core, collapse it into the center, all the magnetic flux has to go there. You have to have a finite magnetic flux trapped in the central region that automatically will form a split magnetic monopole where the magnetic field lines will fan out radially. And that split magnetic monopole is really at the heart of the problem in the ideal MHD limit, because like any monopoles, the field will increase very rapidly towards the center, like the gravity, for example, as 1/r². And the magnetic energy density, of course, is b². It will increase even faster as you approach the center as r⁻⁴. So this increase is faster than most of the energy form that you can think of, including the kinetic energy of the accretion flow. For example, you can estimate based on the free fall. So sooner or later, in this limit, the flow will become magnetically dominated. And if you have a flow dominated by magnetic field, any slight twist of the field line will be able to remove essentially all of the angular momentum you start with. And that's the essential problem with the disk formation. Now, just to remind you that this magnetic break-in is a process that's not avoidable in the magnetized collapse, simply because if you have a piece of gas that's fast rotating because it has already collapsed close to the central axis. It has spun up already, but it's now tied by the field line to the envelope that's yet to collapse. And that slowly moving envelope act like a magnetic brake. The differential rotation between them will twist the field line into a toroidal component, which will act to break the faster rotating piece that's trying to form a disk. And it will transfer angular momentum to the outer massive envelope. And of course, the rate of that would depend very strongly on the magnetic field strength, typically as energy density. So now, if you have a collapse that concentrates matter in this region that you try to form disks, if the magnetic field is very strong here, of course, the magnetic braking will be very efficient. And that's the basic problem. And this has been verified by a number of numerical simulations. But in the simplest illustration that I'm going to give you, we start with a very idealized initial condition, which is actually a generalization of the famous singular isothermal sphere that's scale-free by including both magnetic field and the rotation. The nice thing about this configuration is that if you collapse it, it will still be scale-free. It still be self-similar, which actually provides a very powerful check on your numerically obtained solution. For example, just like in the case of the singular isothermal sphere, the central mass has to increase linearly with time. And this is exactly what we find, the mass and the time. So that gives us some confidence of the numerical solution. Now, in this particular case, as the matter collapses towards the center, the rotation speed is trying to spin up, trying to conserve angular momentum, but it's braked very strongly below the Keplerian speed by the magnetic braking. And this rapid infall, supersonic infall towards the center is another indication that in this particular case, the Keplerian disk is completely suppressed. But in this case, by a magnetic field that is more than 10 times weaker than the critical value. That's actually much, much weaker than half of the critical value that, if you believe in the observers. So I think there's very little doubt that, at least in the ideometric limit, if you have a core that's magnetized to maybe half of the critical value, it will be very difficult to form disks. And this sometimes is called the magnetic braking catastrophe, which in my view should be the starting point of the discussion of the disk formation in strongly magnetized cores. Now, of course, we know that the dense cores are likely ionized, and there are three well-known non-ideometric defects. The ambipolar diffusion usually dominates the other two at the typical core density. Although this depends somewhat on the grain size distribution. If you have a lot of the small grains, like in the medium grains, then the Hall effect could become more important. So let me start with the effect of the ambipolar diffusion. Which ambipolar diffusion will do is to basically allow the magnetic field lines and the ions tied to it to drift relative to the bulk neutral material. So that the net effect is that the magnetic flux that you will drag into the center in the strict ideometry limit now has a chance to escape. And this flux at the center will now be redistributed in the circumstellar region, and in the region that can actually completely dominate the dynamics of the accretion flow. So in this non-rotating calculation, in fact, this magnetic field can almost temporarily stop the nearly free-fall collapse at this so-called the ambipolar diffusion induced shocks that Chris McKee and I found many years ago. So in the post-shock region, this is strongly magnetized region, and it's actually trapped by the run pressure of the accretion. So now if you actually have a very strong magnetic field in a region that's only a few hundred AU, that of course is really bad news for disk formation. So if you redo this calculation, including rotation, you will still see this ambipolar diffusion induced shock here. In the pre-shock region, the matter was still trying to conserve its angular momentum and try to spin up. But once it hits this post-shock region, where the magnetic field is liberated from the central star and invaded that circumstellar region, the rotation speed is 0. So this is almost complete break-in. So mind you that you do produce this very dense, narrow, flat disk, but this disk is not rotationally supported, as you can see by this rapid infall. Now, if you include the other two non-ideal MHD effects, the ohmic dissipation, the Hall effect, the basic picture does not change. For example, you still have this ambipolar diffusion-induced shock here. But there's a very interesting new twist, which is that this post-shock region that's been almost completely braked is now spun up due to the Hall effect. So the rotation speed could be appreciable. And which direction this part will spin up will depend on the orientation of the magnetic field relative to the initial rotation axis. So if you flip the direction of the magnetic field, this inner part will reverse its rotation. So even though this interesting fact that was also discussed by Waldo many years ago is interesting in itself, but it does not, for the typical parameters, it actually does not induce coherent disk. So it looks like these non-ideal MHD effects, at least in 2D, under the assumption of the self-similarity, axis symmetry, does not produce large disks. Now, there was some initial hope that in 3D, maybe things will be different. And the reason for that is that in the region, in this post-shock region, this is highly magnetized region where the magnetic break-in is most severe. That's also the region where the in-fall speed is much lower than the free-fall speed. So this region is actually effectively supported against gravity by the magnetic tension force. And we know that this magnetic support structure in 3D, given enough freedom, it will actually become unstable. And in fact, if you do this calculation in 3D, that's indeed the case. So this is the calculation, including ambipolar diffusion, but looking at the equator, this is density, this is the magnetic field strength. So this is initially laminal, so non-rotating collapse. The inner part will actually become unstable. And so some regions will come in, and the other region will actually expand. Now, this low-density expanding region is actually the region where the magnetic field is the strongest. So this is actually a very strongly magnetized region. And that's actually driven by the magnetic flux, dragged in by the collapse, but it's decoupled at small distances. And now, because of the buildup of the magnetic pressure, it's trying to expand to large distances. So this magnetic interchange instability was first found by my student, Bao Zhao, who is actually in the audience somewhere, who will be looking for a job very soon. Now, unfortunately, this beautiful instability, even though interesting in itself, does not solve the problem. So this is the same calculation, including rotation. So you can sort of see the spirals here. And the basic problem is that the magnetic flux will still be trapped, even though now it has a chance to expand away in some azimuthal directions, but it will still be trapped by the infall, so it will still be hanging around close to the central protostar, create a very strongly magnetized region that will make it very difficult for that rotating accreting material to make full orbit to form a disk. Now, of course, we know that sooner or later, you better be able to form a disk, because we do observe well-developed disks, especially around relatively evolved stars. And so you have to form disks somehow at some point. Otherwise, you and me, of course, will not be here. And there are several proposals to do this, and I think most of these are probably controversial to different degrees. Now, the simplest one, of course, is that if the majority of these dense cores are either non-magnetized at all, or very weakly magnetized, then of course you do not have this magnetic braking problem at all. But I would argue that this is probably not a good option. And the reason is that if you just imagine that if you ask yourself how strong the magnetic field thread in a typical core of one solar mass of, say, 10 to the 4 particle per cc, so that its mass to flux ratio is 5. It's 5 times less than the critical value. And this is a very simple calculation. So it turns out that field strength has to be above 4.5 microgauss. Now that's interesting because this is less than the median field strength that Carl Hayles would tell us for the atomic co-neutral medium. So I think it would be very difficult to make a dense core and demagnetize it to such extent that will be less magnetized than the atomic medium. So I would argue that most of the cores will have at least a magnetic field strength that's 5 times less, 1/5 of the critical value, or lambda less than 5. And such a field strength would still make the formation, at least of the relatively large disks, very difficult. Now, the second option that has been worked out in some detail is the misalignment of the magnetic field direction compared to the rotation axis. Now, there is some plausible motivation for that, and this was talked about yesterday from the karma observation of the magnetic field on the 1000 AU scale. So in this one particular case, you can see that the magnetic field direction is roughly parallel to the direction of the outflow, which of course is usually taken as a proxy for the rotation axis. Of course, that is not guaranteed. But for all the other cases, there is substantial misalignment between these two axes. And in fact, in some cases, up to maybe 90 degrees. So in fact, these authors concluded that these two axes are consistent with being randomly distributed. Now, Juice et al. Was the first to do this carefully. They found that if the magnetic field is very weak, it's 20 times weaker than the critical value, then you can actually form a Keplerian disk no matter what the alignment angle is. But if, on the other hand, the magnetic field strength is half of the critical value, mind you, this is if you believe in the observation by Troll and Crutcher, this is actually typical field strength. Then no matter how large the misalignment angle is, you do not form a Keplerian disk. Now, the interesting case is the actual intermediate case. In this intermediate case, if lambda is several, then if the misalignment angle is large enough, say more than 70 degrees, then you do actually get a disk. So as an illustration, we've done actually similar calculation, but in this case, I will show relatively weak magnetic field. So shown here is a line case, and this is the orthogonal case. So this is the equatorial view. So on the left, so even, again, with very weak magnetic field, you do not form a disk, and the central region is this strongly magnetized lobes that's driven as unstable by the created magnetic flux. Now, on the right, you see a beautiful, beautiful large Keplerian disk. That's the case when you move from the alignment by 90 degrees, so they are orthogonal. Now, the exact reason for this is not clear. It's debated. But in my view, at least one difference between the aligned and orthogonal case is the strength of the outflow driven during this collapse. And this is most clearly seen in the sort of the edge-on view, in the meridian view. So this is the case where you drive a very prominent outflow in the aligned case by presumably the winding of the field. Now, so this outflow could carry away a significant fraction of the angular momentum, so leaving less angular momentum for the collapsing flow to form a disk. Whereas in this orthogonal case, where you do form a disk, there's very little evidence for the outflow. Perhaps the lack of outflow means that there's more angular momentum that will make this formation easier, but this is somewhat controversial. Just a few quick words on the outflow that you do find in a lot of MHD collapse simulations, starting with the pioneering work by Tomisak Saksan. Now, these outflow, by and large, are driven by a combination of the centrifugal force and the magnetic pressure gradient. And the Seifert had a set of nice criterions that will tell you exactly which region will be dominated by the centrifugal acceleration and which region will be dominated by acceleration due to this combination of the magnetic pressure gradient and the centrifugal force. I guess we'll probably hear more about the outflows on Thursday. So I will come back to the main question at hand. Will the misalignment allow you to form large disks or not? Now, we found that if the magnetic field is very weak, say it's 14 or 7 times weaker than the critical value, then indeed you will be able to form nice Keplerian disk if the misalignment angle is relatively large. However, we find that if lambda is 4, which means that if the magnetic field is 4 times weaker than the critical value, which means it's half of the value that's inferred from the observation, then no matter how large the misalignment angle is, you still do not form a large Keplerian disk. So it looks like you need 2 conditions to form a Keplerian disk by this mechanism. First, you need a rather weak magnetic field, and then you need a relatively large misalignment angle. So I think because of you need 2 requirements, that makes it relatively unlikely for the majority of the cores to actually satisfy them. You can actually estimate the fraction of the cores that would satisfy this criterion. Mark Kromholz did that, and we've done that as well. I will not go through all these arguments here, but I think it's probably fair to say that no more than a few tenths of % of the cores will be strongly magnetized, will be so weakly magnetized and have such a large misalignment angle so that you can actually form a Keplerian disk. Now the question is, how does that compare with the observation? Now, we of course know that for the relatively evolved class 0 sources, you do find well-developed large rotationally supported disks. And there's also increasing evidence for well-developed disk around the transition class 1 source. And a very nice recent example is the TMC-1A, where they find the rotation of this circumstellar disk would have a profile that's approximately Keplerian. Now, for the object that you really want to compare with the observations with the simulations is actually the deeply embedded class 0 sources. Now, for those sources, the observational situation is less clear, and of course, for a very good reason, because that little disk is embedded in this very huge, massive envelope, and it's very difficult to untangle the disk from the inner part of the envelope. But nevertheless, there's strong evidence for the mass concentration on small scales coming from the continuum interferometer data. For example, in this particular case of the IRIS-2A in NGC 1333, the fact that the visibility amplitude is roughly constant at large baselines tells you that there's an unresolved component with significant mass, probably more than a couple of % of the solar masses. It could be a small unresolved disk. And such compact emitting component appears to be very common. For example, in serpents, 2 out of 3 class 0 sources appear to have this compact component, which would actually argue for the existence of actually these kind of objects could actually be very common. But on the other hand, Mori et al. Did a nice survey using the Plateau Bureau of the 5 class 0 sources. And they concluded that they do not see any evidence for 100 AU scale large Keplerian disk in their sample. So to clarify the situation, obviously you want to have high resolution kinematic information. And this has been done recently In the case of the L1527, where Tobin et al. Find a nice differential rotation with slow rotating material further away from the central object, faster rotating material closer in, which they think is consistent with a Keplerian profile. Now, there's newer ALMA data some of you probably saw before, which clearly detect the rotation, although the outer part of that rotation is steeper than originally thought by Tobin et al. But nevertheless, the inner part, within about 60 AU, the profile is roughly Keplerian. So I would say that this case for Keplerian disk is reasonably secure for at least this particular source. So really, the question is, how common are these kind of relatively large disks around class 0 sources? So I hope that ALMA will settle this question in the near future. So if it turns out that these relatively large Keplerian disks are actually very rare, and if this object is one out of several, then perhaps very strong magnetic break-in that I talked about before may not be such a big issue. In fact, it may even be desirable because you want the magnetic break-in to keep your disks small, so that if it turns out that these disks are not observable during this phase by ALMA. But if, on the other hand, these large disks are common, then of course we have a big theoretical problem. And some key ingredient must be missing from the models I talked about so far. And a strong candidate for this missing ingredient that has been talked about in the literature, and in fact increasingly, is the turbulence. Now, we of course know that these dense little cores are turbulent with a non-thermal width perhaps at half of the sound speed. Now, this turbulence-enabled disk formation was at least conceptually demonstrated initially by Santos-Limo et al., where they in a toil collapse model that does not form disks in the ideal emission limit, in this case, it turns out that they can form disks relatively easily if you include a substantial amount of turbulence, as in this case. And now this has been found now by a number of groups, including our own. And as an illustration, Banerjee gave me this very nice movie of a low mass core with subsonic turbulence. So initially, basically, this turbulence creates a filament, and this filament collapses very quickly, forms a rotating structure. Now, by the midpoint of the simulation, a well-developed disk forms, and this disk actually will persist to the end of the simulation. So disks do form if you have turbulence in the simulation, for both in this case and in many other cases. Now, why that's the case is still debated. The Santos-Limo et al., they think that maybe all this turbulence will induce reconnection, will change the topology of the magnetic field, would not allow the magnetic flux to be dragged into the disk-forming region. And this is motivated by the earlier analytic work by Lazarian and Vishniak. Now, Seifert et al. Think that the tangling of the field by turbulence perhaps would weaken the magnetic break-in, and also the strong local shear would increase the angular momentum. That, of course, will, at least locally, that, of course, will be beneficial to the disk formation. Now, Juice et al. Emphasize that in a lot of cases, this turbulence actually misaligns the magnetic field with the local direction of the angular momentum, and that is known to have a beneficial effect to the disk formation. And the one thing I would like to caution, one caution, though, is that all these calculations are ideal machine calculations, including our own. So in principle, ideal machine calculation cannot have reconnection. And the reconnection in the simulation happens only when the magnetic field of different polarity is forced into a cell, and they reconnect numerically. So there's some chance that the result will depend very substantially on the numerical resolution, and that has not been explored very carefully. But nevertheless, this turbulence is a very promising mechanism, especially if you find large-scale Capillary disks that are common. If it turns out to be common around the protostars, you do need a mechanism like this to probably explain that. Now, independent of whether large-scale disks are common or not, small-scale, AU-scale disks ought to be common among class 0 sources, and simply because of the powerful outflow, which is actually a defining characteristics of a class 0 sources. Outflows like the one shown here, that's moving at hundreds of kilometers per second, has to be driven very deep from very deep in the potential. Perhaps within 1 AU by some sort of Capillary disk. So it turns out that small AU-scale disks can be formed by the omega dissipation, which is the non-ideal image defect that dominates at the highest density. And this has been demonstrated analytically by Adapt et al., and numerically by Machida et al. And Tomita et al. So the example I'm going to give is the Tomita et al., where they did a really heroic calculation that includes both the radiative feedback, the resistive MHD, and that goes down to the stellar dimension and stellar density. So as you can imagine, this is very difficult, and they were able to carry out this, push that simulation 1 year, one single year, beyond the formation of the stellar core. But during that brief period, they find that they do not form a rotationally supported disk in the ideal image limit, as you would expect, but they do form a small 0.35 AU disk if you include some prescription of the omega resistivity. So this is perhaps the beginning of the disk. And I would love to see how this disk would evolve in time, would grow in time, particularly in the presence of all the other non-ideal image defects. So this will be very difficult to do, but that's what we have to do if we want to solve this problem. But I think one thing that can, in principle, help the disk formation is the removal of the envelope, because after all, it's the slowly rotating envelope that's receiving the angular momentum, that's the magnetic brake. If you can get rid of it somehow at some point, then the inner part perhaps will be free to form the disk. Now, one way to get rid of this envelope, of course, is through outflow, which will presumably, over time, turn a deeply embedded object, class 0 object, into a class 1 object. So my speculation is that maybe the disk will grow very quickly during this transition from class 0 phase to class 1 phase when the envelope is dissipated. But I have not done any honest calculation to back that up, but at least that's something that observers could check very easily. Now, just to summarize, so the take-home message is that the disk formation is not as trivial as you may have thought. And the main problem is the magnetic flux that's been brought in by the accretion, and that's been trapped close to the central star. So in the ideal image limit, that, of course, is the extreme case. You trap all of the flux at the center, which amplifies magnetic field enormously. That makes the disk formation difficult. Now, if you allow the magnetic field to slip relative to matter, so that will invade the circumstellar region. So that will make the circumstellar region strongly magnetized. That actually makes the disk formation worse. Now, this trapped magnetic flux, if in 3D, would tend to escape in some direction, driving this magnetic interchange instability, but they do not go far enough, so you still end up with a strongly magnetized region around the central object. That's the fundamental difficulty with the disk formation. If you want to form a disk in the presence of this strong magnetic field, you basically have only two options. One is to have the material that you want to form disk decouple from this strong magnetic field. Perhaps at high enough density, you can do that with omega resistivity. That might be the origin of the small disk. The second option is to get rid of this trapped magnetic flux altogether. So you wanted to have a reconnection that happens at larger distances so that magnetic flux will not be dragged into that region, and so you do not create that problem. Presumably, you can do that with turbulence, maybe with misalignment, and maybe just in general with complex flow that can force reconnection, numerical or not. So I think we have made a substantial progress in identifying the problem and in identifying maybe some potential solutions. But I think we still have a lot to do. So I will stop there. Thank you.
Thanks for a very clear talk. I see already people lining up. Good. So let's start at the center. Let's use this one and that one. I don't know whether that microphone is working yet. So let's, for safety, use this one and that. We have plenty of one. Yes, okay. Start there. Please state your name.
Yes, Shuichiro Inuzuka, Nagoya University. I'm sorry, but I have to disagree for many points. So
yes, we had communication.
I just pick up one point.
I
just pick up one point.
Okay.
That's important. That is the effect due to the existence of dead zone. Okay.
Yeah.
Dead zone is due to high density. High density means that higher recombination rate, therefore lower ionization degree. That's why it is dead zone. In the dead zone, we can relatively easily form disk, right? You mentioned that is small. However, once we have a dead zone and once we have a small disk, then subsequently accreted material fall onto the region just outside the dead zone, and density in the region just outside dead zone becomes higher, and that region also becomes dead zone. In this way, size of the dead zone increase monotonically, and that becomes actually big, and that can be observed in the simulation for very, very long time calculation, and that is, I think, missing your calculation, but that is shown in our simulation, attributed to our series of simulations starting from 2006.
Okay, let me address that. I do agree that it's possible that this omega dissipation enables small disk would grow through the dead zone. I agree on that point. But what I do not agree is that the calculation so far that went to very late time that allowed the disk to grow to 10 or 100 AU scale. And that, I think, I will have to take a grain of salt there, mostly because in that simulation, I do not see the concentration of the magnetic flux, which omega dissipation does not destroy. It can only redistribute. So that makes me worry about the simulation that runs for a very long time.
No. Omega dissipation can move the magnetic flux from the inner region to the outer region.
Yeah, but it cannot move it very fast, only because in the dead zone, you can decouple magnetic flux. This magnetic flux cannot go very far, but I do not, so it has to be parked very close to the dead zone, by definition almost.
Yes, that's right.
And you have to show me that that region is very strongly magnetized. That did not remove most of the angular momentum before you reach the dead zone.
Oh, no,
if you can actually show me that, I will be convinced. But I did not see that in your calculation.
Okay. And also, in the later phase, loss of the envelope is important. Yes.
Okay, we have that. First. Yes, I was going first there, and then I'm coming to the balcony. Don't worry. Alyssa.
Is this microphone working?
Yes.
Okay. I have a question on behalf of observers.
Okay.
I think it's great that the simulations are getting so much more sophisticated and that there are these sophisticated arguments. There are only some of them that we can solve with observations, and it would be tremendously helpful if some more effort was put into predictions of what would actually be observed. So you have these beautiful, magnetic field lines, and you have flow vectors and velocities and all of this, but we can't measure all of those things. We can measure polarization, which you heard from Huabai is very flawed in terms of how it's weighted, and we can measure particular spectral lines. And so if it would be just fantastic if you could make fake observations.
I will make two observations that would be crucial. One is just the basic observations, trying to find the twisting of the field. So if you have a magnetic field that's twisting, that automatically tells you that that's removing angular momentum. So that's magnetic braking by itself. If you can actually determine, for example, with ALMA, with the cycle 2, you can, if you find twist of magnetic field, then there's no question that the magnetic braking is working on whatever scale that you find twisting. That's the number one. The second observation would be that if you can determine rotation rate from core scale to subcore scale to disk scale, and you can find the specific angular momentum actually decreasing, and if this region is also infalling rapidly, that will be another indication that the magnetic braking is working.
That's great. The second one is easier to measure than the first, and I was trying to specifically say that Paolo Padova was trying to make this point yesterday. When you measure polarization, you don't have sensitivity to the whole line of sight. So if you could put in different assumptions about the sensitivity of polarization and make fake maps, then we can compare that with that.
Okay, that's a good
Thank you.
suggestion.
Okay, I need to make a quick announcement. Irene Sanjose-Garcia, if you can please go to the registration desk. There's an urgent message for you waiting there. Good. Upstairs.
Hi, Mordecai.
Very good. Mordecai Maclow, AMNH. So one cautionary note is that in a disk with MHD, the scale of the turbulence is very, very deep. So we're not resolving almost all of the turbulence. As a result, our numerical models are not even getting close to measuring the actual amount of turbulent diffusion of the magnetic field. So we actually are going to have to develop either sub-grid scale models or some other technique for coupling the actual turbulent diffusion to global disk models before we can actually address this problem. And I think we have to be very careful of saying that the numerical diffusion that we're getting out of these disks has anything to do with the real diffusion in these disks. And there may be plenty of turbulent diffusion simply from magnetorotational instability.
Yeah, I completely agree. I think we are only beginning to explore this problem in the context of the formation of the disk rather than the evolution of the disk once you form a disk.
Okay, is there a second question upstairs? Or not? If not, then we continue here.
Yeah, Günter Wuchtel from Coro at Tautenburg Observatory. I found your SubAU scale disks very inspiring. I mean, not to the pleasure for the observers, I guess, but it's really very inspiring. And I'm reminded of a model by Tamara Rosmaikina and Viktor Safronov, who actually started with this very small disk. Could you remind us of how this fits together with this old PP2 model?
I'm sorry. I may look old, but I'm not that old. I don't remember this. No, I don't know that model. Sorry.
Okay, John?
Oh, so...
State your name, please.
Oh, sorry. John Tobin, NRAO, Charlottesville. So I had, 2 points. So one, I was wondering, do you find it suspicious that the two large disks that we now have resolved and are rotationally supported on class zeros have a magnetic field that's perpendicular to the outflow direction? Do you find that a little suspicious and perhaps suggestive that maybe misaligned magnetic fields are what allows the formation of large disks? And then in your idea of removing the envelope before forming disk, I would worry that you would not have enough mass left to create a disk that is large enough to perhaps form binary stars due to disk fragmentation and so forth.
Right. Excellent question. The first one, the case that I'm familiar with is the case that you studied, the L1527. Indeed, on the Karma scale, which is 1000 AU scale, the magnetic field is perpendicular to the disk. But actually, if you look at the single disk observation on the scale of the core, in fact, the magnetic field is almost parallel to the outflow. So there's a complicated story there. I'm not sure. So that's why, so if that's generally true, if the magnetic field actually is more aligned with the rotation on the core scale, that will make the misalignment mechanism even harder to form disk in the majority of cases. Now, for your second problem, absolutely. So if you want to blow away your envelope and you still want to form a disk, But of course, the envelope would have, say, 1 solar mass. The disk would have 0.1 solar mass, 0.01 maybe. So if only a small fraction of the matter can link around maybe in the equatorial region, that's probably enough to form a minimum solar disk, for example. So it does not take a lot of mass to form the disk. So, but you do have to fine-tune. This is, it's probably gonna not be easy. You probably have to fine-tune the clearing process in order that you have, at the last minute, you have some thing left over that can fall back. This actually reminds me of the fallback disk that my colleague Roger Chevalier developed for the supernova explosion. So that could be, along a similar line.
Yeah, but then this fragmentation of gravitational instability would then be in trouble, and we see evidence of binaries forming on hundreds of AU scales.
I like the theory, but if the theory is in trouble, that's not my problem.
Okay, let's see. Is there any more questions upstairs? Anybody? If not, then a final question down here.
Yeah, Tom McGath, University of Toledo. I'm just asking for a clarification for the observers. When you do these simulations, like in the standard model of protostars, right, the higher angular momentum material comes down later, forming a larger disk. How long do these simulations run? And do you have an idea of sort of the angular momentum distribution and how this depends on sort of the total amount of angular momentum in the envelope?
There may be different ways of defining it. If you put in more physics, the more physics that you put in, the shorter you run the simulation. And we have seen one example. You can run 1 year, physical year, past the simulation. But if you remove some of the physics constraints, then you can run the simulation longer at the risk of maybe producing a result that may not be completely trustworthy. But I would actually turn the question around, because the most important problem for this formation is actually the initial condition. It's the distribution, is how fast these cores are rotating, how strong these cores are magnetized. And that I actually would ask my observer friends to actually tell us before we put that into the computer.
Okay, good. Very quick.
Just a comment to Tom's question here. So these simulations, they can run up to 10,000 of years. And what we see, interesting enough, is that we get quite a flip of the angular momentum. So the disk can be warped, and also the angle between the magnetic field and the rotation axis also changes over time. So that's not a clear prediction what you would expect observationally. You have to do more statistic actually on this, and to see what would be the typical outcome there.
Okay, good. Well, I think we heard a lot about the models. When we had a meeting in Hawaii in April, I made the statement that let the ALMA data speak for themselves, rather than trusting all the beautiful simulations. And I have seen already several posters up there on actually ALMA data that show actually rotationally supported disks, even in the class 0 phase. So I think this is a very interesting topic that will surely develop in the coming years between Protostars and Planet 6 and 7. So let's thank the speaker again.